Okay, let's look at this problem right here. 30 kilogram disc shown is pin supported at its center. Let's figure out the angle it must rotate in order to get a velocity of 2 radians per second, starting from rest. It's acted on by this moment, this 5 Newton meter moment. Spring is originally on stretch, and its cord wraps around the rim of the disc. All right, so we know that we're gonna use our work energy method or conservation of energy method. This is a rigid body, right? It's a disc that has some size and dimensions. And so I always just start with my conservation of energy equation, right? The potential energy initial plus kinetic energy initial plus any non-conserved work, like a force times distance or a moment times a theta, equals all the final potential energy and the final kinetic energy. And I even like to write out all these. Don't forget spring and gravity, right? Potential energy could be the potential energy in a spring and potential energy due to gravity. Kinetic energy, it could be linear or rotational kinetic energy, right? The linear 1/2 mv squared, and also the rotational 1/2 I omega squared. And also this non-conserved work, I'm thinking FD or M thetas. I even like to just write out the whole equation. 1/2 kx squared is potential energy in a spring. mgh is potential energy due to gravity. 1/2 mv squared is the kinetic energy in the linear velocity. 1/2 I omega squared is the kinetic energy due to rotational velocity, plus FD plus M theta equals all of this final 1/2 kx squared final mgh final 1/2 mv squared final 1/2 I omega squared final. So you probably don't have to write out the whole equation every time, but I like to, and that's a good first step. If you're not sure where to get started, why not go ahead and write it out, step back and look at that equation, and then let's break it up into bite-sized pieces so that you can tackle this equation. A lot of this is going to go to zero. Some of it you didn't even have to write, but I like to write out the whole thing and then set a lot of things to zero. All right. It says starting from rest. So starting right from rest, and that 1/2 mv squared and 1/2 I omega squared on the left-hand side, the initial, is going to be equal to 0. Okay. So now let's kind of look at the spring. Let's look at the spring initial, the spring final. Initially, it is unstretched, and so if it's unstretched, its x is 0. Remember, x is not the length of the spring, x is the amount of stretch or compression of the spring. And so if it's not stretched or compressed initially, then that x would be 0. But I think we are going to have this 1/2 kx squared final, right? I can visualize this. That spring is going to stretch because it's getting wrapped around that disc. All right, let's think about MGH. This is the MGH, and I also like to write, remember, this is the H of point G. This is the H of point G. This is the velocity of point G. This is the I of G. So let's write those G's to remind ourselves, the height of what? The height of the center of gravity of the object that has weight, the object that has mass. So it's not the center of like that spring. Normally the springs have negligible mass compared to the mass of our other objects. That's the center of gravity of the disc. That point right there, they're calling it point O. I'm calling it point G. So that's the MGH of point G. So think about where that starts and where that point ends. Does that point change in height? No. And so there's no change in MGH. We can just set that. That's my 0 height. So this is 0, okay, because that's pinned right there. That point G is not moving up or down. Okay. Is there any external force that is acting a distance. So sometimes it's helpful to draw a free body diagram of this. If I was to draw a free body diagram, I would have the force in a spring, but we already take that into consideration. I would have the force due to weight. We already have accounted for that. I would have the force of that pin right there. Maybe I'd call it OX and OY. So yeah, I would have force OX and OY, but are either of those forces actually acting a certain distance? No, there's no FD for this problem, right? There's no external force that's actually acting a certain distance. But there is a moment, and I think it is rotating a distance theta. So we do have that term. And then finally, it's moving. It actually achieves an angular velocity of 2. It's telling us that right there is 2. What is this velocity? Sorry, right here. That's the velocity of point G. Think about point G. Is point G actually moving? No, point G is just stuck right there. So that is 0 also. Or remember that V equals R omega, but this R is the distance from the center of rotation to point G, so this would be 0, right? The point G is at the center of rotation. Point G is not moving. So there is no 1/2 mv squared, but there is a 1/2 I omega squared. So I think that's as simplified as our equation is going to get. So that's 0, 0, 0, 0, 0. Let's see, on the left-hand side, the only thing we have is a moment of 5 Newton meters acting a distance of theta. I don't know theta, didn't tell me theta, and actually it's asking for determine the angle theta. So I have to determine theta. So that's all we have on the left-hand side. The right-hand side, we have 1/2 K, 10 newtons per meter. X. Do I know X? X is the amount of stretch of that spring. Do I know how much that spring is stretched? Not sure. I'll come back to that. Let me just put X right here for now. Plus 1/2 I. The I of a disk. Sometimes it'll tell you the radius of gyration. If it tells you the radius of gyration, then I is K squared times M. It doesn't tell us that, so I think we can assume that it's a uniform cylinder, uniform disk. The equation for a uniform cylinder, I about the center of a cylinder, is 1/2 m r squared, and so that's what we're going to use. Now, a lot of times you might have 2 of these 1/2. That's fine. All right, so that 1/2 right that I've already written is from the equation. Then my I is 1/2 m r of 0.2 squared, and then I have omega squared. All right, so be careful. Don't leave out one of those 1/2s. Don't forget to square, both of these. I like to put these brackets right here for my I. That's my moment of inertia. So there we go. I didn't really keep up with my units, but my units are fine. Everything's in newtons, everything's in meters, everything's in radians per second, meters per second squared, things like that. Okay. So now let's see. I've got two unknowns, but I only have one equation. I cannot solve for both of those with just one equation. So have I forgotten anything, or are they related? Do you think that X, the amount of stretch in the spring, is related to the angle? That's the angular displacement. The angle that it twists. The amount of stretch. Can you visualize this, that this spring is going to get wrapped around the edge of that disc, and so this, does that look like an arc? This arc length would be the amount of stretch in my spring. Is that related to theta? There's the theta. Remember, so arc length. Remember definition of arc length, S equals r theta. So in this case, x equals r theta. X equals 0.2 theta. So right here, I'm going to plug in 0.2 theta right there for my x. Don't forget, I'm going to plug it in inside this parentheses. Don't forget to square that theta. Looks like I'm going to have a theta squared and a theta and a constant. Have to use quadratic formula to solve for this. I think you can do that, right? Skipping the math, theta is 0.24 radians, and so that's my answer. I could change that to degrees if I wanted to. Remember, though, in these equations, your theta is always in radians. I think I'll just leave it. It says what determine the angle through which it must rotate. All right, 0.24 radians. That's my angle that it rotates.